Hello, today I'm going to talk about the simple harmonic motion. It's a physics course, introductory physics for university, first year university, community colleges, whatever, something like that. So it's a simple harmonic motion. To understand this in very basic things, I'm not going to go in like a lot of details about it. Let's say we have a mass M connected to a spring, and that spring connected to fixed arm or to the wall or whatever. That spring has a constant, we call it the spring constant K. K has a unit of, K is the spring constant, has a unit of Newton per meter. And the meaning of this, how many newtons we need to extend or to press that spring 1 meter. That's the meaning of the spring constant. Now, and this is the position. Let's say this is the initial position when there is no force applied on this mass. And we could set x naught to 0 meter to make it easy. I'll show you how to make, why this one is going to help us to make it easy. But we can set it to any value we like. Then if we pull it by a force F, then this spring is going to be extended some amount of length, and that maximum value of length can be called, so this is the farthest place that the mass can go. So this place, so the distance from the equilibrium to that one, this is x max. X max is, let's say, 2 meters, 2 millimeters, anything, it's just a number. And then when we release it, the object is going to come back to the initial position by the something we call restoring force. That's Hooke's law. And then with the continuity or the inertia, Newton's first law, that the object is going to continue moving towards this point, like moving away from the equilibrium point. And then it's going to reach the farthest place from the negative side. Then this distance again is x max. So we could label this as negative x max. This is 0, this is positive x max. So if this is a 3, this is negative 3, 0, 3, for example, something like that. Okay? Now, of course, let's say there is no friction between the object and the surface, there is no friction between the object and the air, and this object can continue with simple harmonic motion. That's the meaning of why I call it simple harmonic motion. There is no friction, there is no dumping in our movement. If we set this experiment, for example, and then the position as a function of time, so when t equal to 0, let's say we pull it and then we start our time. So when t equals 0 second, this one expressed in second, this one is expressed in meter. Then the position equal to x max, whatever the value, that's more general. And we know when, like the simple pendulum, same thing, that when the object releases from the farthest place, passing through equilibrium, come to the negative place, and then back to the equilibrium, and then to the farthest place. After that, the movement is going to repeat itself. That's the meaning of oscillation motion. When it's going to repeat itself, that the time required to finish one circle, we call it period. That's the definition of the period. So when the time equals to half of the period, it means the object has to be in this position, negative x max. And between them, when the time equals 1/4 of the period, the object at 0 position. And then when the object need a period to go back to x max, and between this and that's 3/4 of, let me put t down here, that's x max, and then 3/4 of the period, the object will go back in this. Now, if we need to visualize this or sketch it, this is the time expressed in seconds, that's the position expressed in meter. Okay? Then we get something like that. This is cos theta, trigonometric function. So cos theta, this is like, as I said, simply, I don't want to go on any more details. So now we are able to express the movement in a function. As soon as we get the function, then we can get anything we like. And I'm going to show you how to get the other physical quantities from that. So from this part, I just want to write that from these we can say x as a function, that's the position as a function of time, equals to some constant, we call it the amplitude of the motion itself, the wave, and then multiplied by cos some angle, and that angle is omega t. Omega is the frequency, like angular frequency of the movement. Now, if someone said, okay, why you assume that when t equals 0, we have to be at that position? Why we can't be in this or that or something between? So we have a wide range from x max to negative x max, and we can start our stop time from any position we like. It's okay, we can do that, but we need to add some correction, an angle, we call it the phase angle. That's the phase angle. This is a constant for any specific wave. Omega is constant, the only variable is t. That's why position is a function of time. So I'm going to erase these and get the other physical quantity. If we have position function of time, then it's very easy to get the velocity as a function of time, which is the first derivative of the position with respect to what? To t. I like to write the derivative in this way. I don't like to write like dx dt. I want to emphasize that d dt is an operator, act or hit the function to give me another function. That constant is going to be as is. Derivative of cos, that's sine. The angle is omega t plus phi, but we know derivative of cos is negative sine, so that's negative. And then the derivative of the angle itself is just omega, and the derivative of phi is 0 because it's a constant. So we get the velocity. Now this is the velocity of the simple harmonic motion. So the velocity equal to negative these two constants. We could express them or replace them by one single constant, which is V max, because the unit of that sine has no unit. Sine omega t plus phi. So that's the velocity of the simple harmonic motion. This is a good equation. We can use it like V max equal to omega x max. If we have amplitude and frequency, we can get the maximum velocity. If we have maximum velocity and maximum displacement, then we could get the frequency of the object, whatever it's useful. The other thing we derive one more time, we derive the velocity with respect to time. That's v of t equal to, so the negative as is, and omega, I'm going to write it back in terms of omega x max. I'll tell you why in a second. And then the derivative of sine is cos omega t plus phi, and then the derivative of the angle is omega. So omega times omega, that's omega squared. What is that? That's the acceleration itself of the object, equal to negative omega squared. Now what's left is x max cos omega t plus phi. If you compare it to this equation, that's the position itself. So that's x of t. Okay? The acceleration equals to the position itself multiplied by the square of the frequency. Yeah, we could, then since we get position, velocity, acceleration, then we can get the energy. Like for example, the kinetic energy. The kinetic energy equal to 1/2 mv squared, right? 1/2 m, this is constant, doing nothing, it's just constant, it's not scary. V squared, we have V, then square this thing. Then we get the kinetic energy of the wave itself. We can get the potential energy also by using the position itself. Like 1/2 kx squared, and then x is this, we square it. And then we can find the relation between these, the total energy, called kinetic energy. As I said, this is just fundamental and basic ideas about the simple harmonic motion. Thank you so much, and have a nice day.